At 6:05 on an August evening, commuters crossed a Minneapolis bridge that had already failed 40 years before. On paper, in a calculation, nobody had gone back to check. Every video on this channel starts the same way, with a structure that looked fine right up until it wasn't, and the I-35W bridge in Minneapolis is one of the cleanest examples we have covered. It carried traffic for 40 years, and buried in the settlement that followed the collapse is a number that will surprise you. We will get to it later. You need to understand what a fracture-critical bridge is first, because that one design choice explains almost everything that follows. The Twin Cities built much of their identity around the Mississippi River, and by the 1960s, Interstate 35W was one of the main arteries linking Minneapolis to its northern suburbs. The crossing near St. Anthony Falls needed a bridge built to carry heavy traffic for generations, not just get built and forgotten. City and state planners treated the project as a point of pride, a symbol of post-war American engineering confidence. That confidence is exactly what makes this story worth telling, because nobody involved thought they were taking a risk. Construction on the new I-35W bridge began in 1964, designed by Sverdrup and Parcel and Associates of St. Louis, a respected name in American bridge building. Crews built a steel deck truss, a style chosen because it could span the river without a pier in the main channel, keeping it clear for barge traffic. The design passed the standard review process of the era without objection. Nobody flagged a problem, because on paper, everything about it checked out. A steel deck truss bridge like this one is what engineers call fracture critical, meaning load travels through a limited number of connected members with no backup path. If one main component fails, nothing else in the structure is ready to catch that load. Redundant designs spread weight across multiple paths, so a single bad part is an inconvenience. A fracture-critical design has no such safety net, so every connection has to be exactly as strong as the math says, for the life of the bridge. The connections holding a steel truss together are gusset plates, flat steel plates bolted or riveted at each joint where beams meet, distributing force between them like the knuckles of a skeleton. The I-35W bridge had dozens of these plates, most doing their job quietly for decades. Engineers calculate exactly how thick each plate needs to be, using formulas that account for deck weight, traffic, and a safety margin on top. Get that calculation wrong once, and it stays wrong until somebody checks it again. The I-35W bridge opened to traffic in 1967, carrying commuters smoothly across the Mississippi River for the first time. Local papers covered it as a modern convenience, another piece of the interstate system linking Minneapolis to the rest of the country. Drivers crossed it every day without a second thought, the way people do with infrastructure that simply works. Somewhere inside that structure, at a joint engineers would later label U10, the steel was already thinner than the math actually required. Investigators later determined that several of the bridge's gusset plates, including the ones at node U10 near the center span, were built at about half an inch thick. Recalculation showed the loads at those points called for something closer to a full inch of steel. That is not a rounding error. That is a plate carrying roughly half the strength it needed from day one. The structure did not fail the moment it opened, because the original traffic loads left just enough margin to get away with it for a while. Design errors like this do not survive because nobody is watching. They survive because everybody assumes somebody else already checked. Sverdrup and Parcel's internal review did not catch the discrepancy, and the state agency approving the plans relied on the design firm's own calculations rather than re-deriving every load path from scratch. That is not unusual. It is how engineering has always built on trust in the paperwork that came before. The structure did not fail, the decisions did, and the first was simply not looking closely enough at one set of numbers. For the first several years after 1967, the bridge behaved exactly as every successful bridge behaves, meaning it did nothing dramatic at all. Crews performed routine maintenance, and inspectors walked the truss looking for rust, cracked welds, and corrosion, the things a visual inspection is built to catch. None of those checks were designed to re-verify a decades-old calculation buried in a design firm's file cabinet. The bridge was, by every visible measure available at the time, a normal, healthy piece of infrastructure. At some point in the 1970s, Minnesota's highway department resurfaced the bridge deck with an added layer of concrete, standard maintenance meant to extend the roadway's life. Nobody saw this as risky, because resurfacing bridges is routine work performed on interstates nationwide every year. But concrete is heavy, and every inch poured onto that deck became permanent weight the truss below had to carry for the rest of its life. On a bridge with adequate margin, an overlay like this is a non-event. On this one, it was the first quiet withdrawal from an account that was already low. Engineers separate a bridge's load into two categories: dead load, the permanent weight of the deck, the railings, and anything bolted on for good, and live load, the traffic passing over it at any given moment. A bridge is designed with a calculated buffer above both combined, meant to absorb surprises. Every pound of concrete added after 1967 ate into that buffer as dead load permanently, whether a single car was on the bridge or not. Unlike traffic, which comes and goes, added dead load never leaves. In 1990, federal inspectors classified the I-35W bridge as structurally deficient, a label that would later dominate headlines after the collapse. At the time, it barely made local news because the rating reflected corrosion on the bridge's bearings and general wear, the kind of finding that triggers a maintenance plan, not an evacuation. MNDOT kept running the bridge under normal traffic, scheduling repairs the way agencies do with thousands of similar bridges nationwide. The label sounded alarming in hindsight, but in 1990 it meant something much narrower than most people assume. This is the part worth slowing down for because it is the single most common misunderstanding about this collapse. A structurally deficient rating does not mean a bridge is about to fall down. It means specific elements need repair or monitoring, full stop. It is a maintenance category, not a collapse warning, and conflating the two makes for a simpler headline but a less accurate one. The rating that followed I-35W for 17 years had nothing to do with the Gusset Plates at node U10, the flaw that actually brought it down. The I-35W bridge was never unique for carrying that structurally deficient label, and that is the uncomfortable part. In any given year, thousands of bridges across the United States carry the same designation, spanning rivers and highways millions cross without a second thought. Most of them are exactly what the label implies: aging structures needing attention, not secretly hiding a fatal design error. From the outside, a bridge with a fixable maintenance issue and one with an invisible calculation error look identical, and only one of them is a ticking clock. In 1998, the bridge received a second concrete resurfacing project, adding another layer of permanent weight on top of the 1970s overlay. Again, nobody treated this as controversial, because on paper, resurfacing a highway bridge is exactly the responsible maintenance taxpayers expect. The math connecting these repaving projects to the undersized Gusset Plates from 1965 simply was not run again because nobody had reason to think it needed to be. Two ordinary maintenance decisions, 30 years apart, were quietly stacking weight on top of a flaw nobody yet knew existed. When federal investigators reconstructed the bridge's full load history after the collapse, They calculated that the accumulated overlays had added roughly 20% more permanent dead load than the original 1967 design ever accounted for. 20% does not sound catastrophic on its own, and on a bridge with a healthy margin, it probably would not have been. But this bridge never had a healthy margin at node U10, thanks to gusset plates already carrying more than their calculated capacity from day one. Every added inch of concrete was closing a gap that should never have existed. In the early 2000s, engineers reviewing the bridge flagged fatigue cracking in some steel members, the kind of finding that prompts additional inspections rather than panic. University-affiliated researchers and MNDOT engineers discussed reinforcement options, weighing whether the aging truss needed upgrades beyond routine maintenance. This was, in some ways, the closest the system came to catching the underlying problem before it turned fatal. But fatigue cracking and undersized gusset plates are different failure modes entirely, and the era's inspections were built to look for one, not the other. In 2003, MNDOT contracted URS Corporation, a firm that had absorbed the legacy of the original design company, to study the bridge and evaluate reinforcement options. This was exactly the kind of proactive step a responsible transportation agency is supposed to take with an aging fracture-critical structure. URS engineers reviewed drawings, inspected the truss, and modeled potential retrofits, work that looks, from the outside, like due diligence done correctly. They built it anyway on the original foundation of assumptions from 1965, and that is where the story gets interesting. URS Corporation's review focused on fatigue cracking, corrosion, and reinforcement strategies, reasonable priorities given what the visible evidence pointed toward. What their study did not include was an independent, ground-up recalculation of the 1965 gusset plate capacity at every node, because nobody suspected the original design math itself was flawed. Every engineer involved was working from the reasonable assumption that a bridge standing successfully for nearly 40 years had already proven its own calculations correct. That assumption, reasonable as it sounds, is exactly the gap this story lives inside. By the summer of 2007, MDOT had a new resurfacing and repair project underway on the I-35W bridge, replacing lighting, repairing guardrails, and repaving sections of the deck. Construction crews became a regular presence that summer, closing lanes and shifting traffic patterns. From the driver's seat, this looked like any other summer construction zone on any other American interstate, mildly annoying and unremarkable. Every collapse has a paper trail. You just have to know where to look, and by August, that paper trail was about to collide with the physical world. As part of that summer's work, crews staged sand, gravel, and heavy equipment directly on the bridge deck, positioned near the center span for an upcoming concrete pour. Investigators later estimated the staged materials added several 100,000 pounds of concentrated weight sitting almost directly above node U10, the exact joint where undersized plates had carried an inadequate margin for 40 years. None of the crews had any way of knowing that, because nobody working that summer had ever been told the plates there were undersized. The stage was set, quite literally, for the afternoon of August 1. August 1, 2007 began as an entirely ordinary Wednesday in Minneapolis, warm and clear, the kind of late summer day that gives no warning of anything at all. Commuters left for work the same way they had for years, many crossing the I-35W bridge without giving the construction zone more than a passing thought. Crews arrived to continue the resurfacing work already underway, moving equipment into position for the day's tasks. Nothing about the morning suggested this would be the day 40 years of decisions finally caught up with a single steel joint. By late afternoon, traffic had built into its usual rush hour crush, commuters heading home, delivery trucks, a fuel tanker, and a school bus carrying children from a Minneapolis day camp returning from an outing. Roughly 111 vehicles were on the bridge deck as the clock approached 6 p.m., an ordinary snapshot of an American city ending its workday. Above the river, the truss carried all of it exactly the way it had for 40 years, except this time the margin at node U10 had finally run out. At approximately 6:05 p.m., the Gusset Plates at node U10 finally gave way under a load they had never actually been strong enough to carry. A construction surveillance camera and nearby witnesses captured what happened next, the center span dropping away in a matter of seconds, steel and concrete twisting downward toward the Mississippi River. There was no slow sag, no gradual warning, because a fracture-critical structure fails all at once when its one load path finally breaks. The structure did not fail. The decisions did 40 years earlier, and the bill came due in under 10 seconds. Sections of the deck plunged dozens of feet into the Mississippi River and onto the riverbank below, carrying vehicles down with the collapsing structure. A fuel tanker caught fire on the wreckage, sending black smoke over the river as dust from the broken concrete settled over the scene. Cars that had been mid-crossing seconds earlier now sat tilted on broken slabs of roadway, some partially submerged. In under a minute, one of the busiest interstate crossings in Minneapolis had become a disaster zone, and the response that followed would define the rest of the summer. Within minutes, off-duty firefighters, boaters, and construction workers from the resurfacing crew were already wading into the water to help people out of vehicles, well before emergency crews reached the scene. Minneapolis police and fire launched a full rescue operation, treating the riverbank as an active disaster site while divers searched for anyone trapped in submerged cars. Governor Tim Pawlenty declared a state of emergency within hours. Is there a bridge or overpass near you that you quietly do not trust every time you cross it? I would like to hear about it in the comments. For the people still on that bridge, the next few minutes would decide everything. On the collapse section sat a school bus carrying dozens of children from a Minneapolis day camp, tilted on broken pavement not far from the tanker fire. The driver and an adult counselor moved quickly, guiding children off the bus and away from the wreckage, while nearby workers helped lift kids over broken concrete and twisted rebar. Every single child on that bus survived. It remains one of the details people remember most vividly about August 1, 2007. A small mercy inside a genuine catastrophe, and not the only surprising outcome this story still has waiting. As rescue crews worked through the night and into the following days, the scale of the tragedy became clear. And remember, that settlement number mentioned earlier is still coming. It is worth the wait. For now, the immediate math was grim enough on its own, measured in lives and injuries rather than dollars. Divers continued searching the river for missing vehicles for days after the collapse, a grim, methodical process far removed from the chaos of the first hour. What investigators would piece together from the wreckage itself would take more than a year to fully explain. When the final count came in, 13 people had been killed and approximately 145 more were injured out of the roughly 111 vehicles on the bridge deck at the moment it gave way. Those numbers alone made it one of the deadliest bridge collapses in modern American history, turning a regional story into a national one overnight. Every figure traces back to the same point of failure, a joint the width of a dinner plate quietly overloaded since 1967. This was not bad luck. This was a series of choices, and the investigation was about to expose every one of them. The National Transportation Safety Board opened a full investigation within days, treating the collapse as one of the most significant bridge failures in the agency's history, given the casualties and the interstate's national importance. Investigators secured the wreckage site and began the slow, methodical process of documenting every piece of steel exactly where it had landed. This would not be a quick inquiry, because a fracture-critical failure like this could have originated at any of dozens of connection points. Every collapse has a paper trail. You just have to know where to look. And this time it ran straight through the bottom of the Mississippi River. Recovering the wreckage was a massive operation in its own right, requiring cranes, barges, and divers to lift hundreds of tons of twisted steel out of the river without destroying evidence. Each major component was tagged, photographed, and moved to a secured lot to be laid out and studied like pieces of a shattered puzzle. The work took months, running into the fall of 2007, as investigators pieced together which member failed first. Somewhere in that field of recovered steel sat the answer to why 40 years of traffic had suddenly become too much. In a secured lot near the site, investigators laid out recovered truss sections in something close to their original configuration, essentially rebuilding a life-size map of the bridge's skeleton on dry ground. This let engineers compare damage patterns across dozens of joints to figure out which failed first and which broke as a consequence. It is painstaking, unglamorous work, the opposite of the dramatic collapse footage that made national news. But it is exactly this kind of quiet forensic reconstruction that eventually points a finger at one single joint. As the reconstruction progressed, investigators ruled out corrosion, welding defects, and material quality as the primary cause, none matching the damage pattern in the wreckage. Instead, the evidence kept pointing toward the connections themselves. The gusset plates joining the diagonal and vertical members of the truss. Deformation patterns on certain plates suggested they had bent and buckled under stress before the surrounding steel gave way, a telltale sign in structural forensics. The investigation was closing in on the exact geography of the failure, narrowing a bridge nearly 2,000 feet long to a handful of suspect joints. To confirm what the physical evidence suggested, NTSB engineers built detailed computer models of the truss, simulating how load moved through the structure under the exact conditions present on August 1, including the overlays and staged materials. Running those simulations let investigators test specific failure theories without guessing, comparing predicted stress against the deformation seen in the recovered steel. The models kept returning the same answer, no matter how the inputs were adjusted. One joint, more than any other, was carrying far more stress than its design ever accounted for. That joint was node U10, a gusset plate connection near the center of the span, close to where the resurfacing crew had staged its sand, gravel, and equipment that afternoon. Investigators determined this was the origin point of the collapse, the single connection where failure began before cascading through the rest of the fracture-critical structure in seconds. Once U10 gave way, the truss had no alternate path to redistribute that load, and the collapse became essentially unstoppable. Finding the origin point was a milestone, but investigators still needed to explain why U10 had been the weak link all along. When investigators pulled the original 1965 design calculations and compared them against the as-built gusset plates recovered from node U10, the mismatch was unmistakable. The plates in the ground were thinner than the load requirements called for, a discrepancy that had nothing to do with corrosion or anything that happened after 1967. This was a mistake made at the drafting table decades earlier, sitting in the structure since the day it opened, waiting for the right weight to finally expose it. The engineering was the last thing to go wrong. Everything else had gone wrong first, quietly, for 40 years. Here is the number that frames this entire investigation. From the bridge's opening in 1967 to its collapse in 2007, the undersized gusset plates at node U10 sat inside that structure, carrying traffic and passing every visual check anyone ever performed. For exactly 40 years, no amount of routine maintenance could have caught it, because the flaw was never something you could see, it was something you had to recalculate. 40 years is a long time for a mistake to hide in plain sight, and it is the exact length of time this channel's title promised you at the start. Investigators were careful to rule out the explanations the public initially assumed, because it would have been easy to blame an old, rusting bridge and move on. But metallurgical analysis of the recovered gusset plates showed no corrosion damage significant enough to explain the failure, and no evidence of a fabrication defect from the steel mill either. The plates were exactly what the 1965 drawing specified, which was itself the problem, because what the drawing specified had never been enough. This was not bad luck. This was a series of choices made by people who trusted numbers nobody ever went back to test. By late 2008, the NTSB had assembled the full chain of contributing factors into a single narrative anyone could follow. It started with gusset plates designed too thin in 1965, then 2 rounds of concrete resurfacing quietly added roughly 20% more permanent weight on top, and finally on August 2007, construction equipment staged directly above node U10 provided the final push past the structure's remaining capacity. Remove any one factor, and the bridge likely stands today. Stack all 4 together, across 4 decades, and collapse became less a possibility and more a matter of time. The staged materials did not create the underlying weakness, but they were the final, concentrated load that pushed node U10 past whatever capacity it had left. Investigators estimated the sand, gravel, and equipment positioned that day added substantial, localized weight directly above the already compromised joint, at the worst possible moment in the worst possible location. It is a detail that resists a simple villain, because the crew doing that work had no way of knowing what sat beneath their equipment. They were performing ordinary maintenance on a structure everyone believed was sound, the same story that had played out with every overlay before it. By the fall of 2008, more than a year after the collapse, NTSB investigators had moved from gathering evidence to writing conclusions, cross-checking their models against the physical wreckage one final time before going public. Families of the victims and survivors of that evening had waited more than a year for an official explanation. Minnesota's Transportation Department, along with engineering firms connected to the original design, waited too, knowing the findings would carry serious legal and financial consequences. What the report said next would reshape how bridges are inspected across the entire country. In November 2008, the NTSB released its final report, naming the undersized gusset plates at node U10 as the probable cause, with the added dead load from decades of resurfacing and the concentrated construction load on August 1 listed as contributing factors. The report was unusually direct, tracing the failure to a specific engineering calculation made in 1965 rather than vague notions of an aging bridge. For MNDOT, the design firm's corporate successors, and engineers nationwide managing similar structures, the message was blunt. This was not bad luck. This was a series of choices, and now they were on the public record. The report's findings did not stay contained to Minnesota. Transportation departments across the United States began reviewing their own fracture-critical bridges, aware for the first time that a design calculation error, not just visible decay, could be sitting undetected inside a structure they had trusted for decades. Engineers who had spent careers assuming original design work was settled fact were now being asked to question it. It was an uncomfortable moment for a profession built on trusting the paperwork that came before, and it forced a reckoning that reached far beyond one bridge in Minneapolis. In direct response to the I-35W findings, federal guidance began requiring states to identify their fracture-critical bridges and prioritize load capacity reviews of gusset plates, a practice that had never been standard before 2007. Inspectors were now expected to go beyond looking for rust and cracks, actively re-verifying decades-old calculations rather than assuming they still held. It was a fundamental shift in how bridge safety worked in America, moving from purely visual inspection toward periodically retesting the math itself. That shift did not undo what happened in Minneapolis, but it meant the next hidden error had a real chance of being caught before it mattered. Even as the investigation continued, Minnesota moved fast to rebuild. The new I-35W St. Anthony Falls Bridge opened to traffic on September 18, 2008, roughly 13 months after the collapse, built under a design-build contract that compressed years of typical construction into little more than a year. For a city that had watched its interstate crossing fall into the river on live television, reopening that quickly carried enormous symbolic weight. But speed was only half the story, because the new bridge also had to be engineered so the exact failure mode that doomed its predecessor could never happen again. The replacement bridge was designed with genuine structural redundancy, multiple load paths, so that no single connection failure could cascade into a total collapse the way Node U10 had. Engineers also embedded structural health monitoring sensors directly into the concrete and steel, continuously tracking strain, temperature, and movement so problems could be detected in real time rather than discovered decades later by accident. It was, in a very real sense, the profession answering its own 40-year-old mistake with the opposite design philosophy. The old bridge hid its flaw. The new one was built to announce any weakness the moment it appeared. Rebuilding the crossing came with a price tag of approximately $234 million, funded through a combination of state and federal transportation dollars and delivered under a contract structure that rewarded the builder for finishing early. That figure covered not just replacing what had been lost, but building in the redundancy and monitoring technology the original bridge never had. For a state transportation budget, it was an enormous single expenditure. But set against 13 lives and the legal battles still to come, it was by comparison the cheapest part of this entire story. Here is the number mentioned earlier, the one buried in the aftermath. In 2008, the Minnesota State Legislature approved a compensation fund of approximately $38 million for the victims and families, an unusually direct acknowledgement that the state's own oversight had contributed to what happened. It was not a courtroom verdict, it was a legislative decision, the state effectively settling with its own residents before the lawsuits against the engineering firms had even finished. That fund closed one chapter of accountability. The next chapter belonged to the private companies whose calculations started this entire story. The state pursued its own legal claim against URS Corporation, the firm that had inherited the original design company's legacy and had been hired in 2003 to study the very bridge that later collapsed. In 2010, that litigation ended in a settlement reported at roughly $52 million, one of the larger sums connected to the disaster, reflecting the firm's link to both the flawed calculations and a missed opportunity to catch them decades later. URS never admitted the design error was theirs outright, but the settlement spoke plainly enough. Every collapse has a paper trail, and this time it led straight into a courtroom. Additional, smaller settlements followed from other companies connected to the bridge's design lineage, and the contractor performing the 2007 resurfacing work, closing out the legal reckoning piece by piece over the following years. None of those payments could undo what happened on August 1, 2007, and nobody involved ever pretended otherwise. What the settlements did accomplish was rare, a documented dollar figure admission that the failure traced back to specific corporate decisions rather than an act of nature nobody could have prevented. The financial chapter of this story eventually closed. The engineering lesson never did. It is worth saying plainly, one more time, because it is the detail most people still get wrong about this bridge. It was not old age. It was not simple neglect. It was not corrosion eating away at rusted steel over 4 decades, the image most people picture when they hear the word collapse. It was arithmetic, a load calculation performed in 1965 that was wrong from the start, sitting quietly inside the structure until enough weight finally exposed it. The structure did not fail. The decisions did, and every one of those decisions can be traced, dated, and named. The lasting lesson for the engineering profession was not really about Gusset Plates specifically. It was about the danger of treating any old calculation as permanently settled. A bridge that has stood successfully for decades feels like proof its original design was correct. But standing under one set of conditions is not the same as being verified safe under every condition that follows, including new weight added years later. Since 2007, engineers reviewing aging infrastructure are far more likely to ask an uncomfortable question before approving new work. What if the original math was never quite right? That single habit, more than any new regulation, may be the collapse's most lasting legacy. That lesson resurfaced in the public conversation again in March 2024, when the Francis Scott Key Bridge in Baltimore collapsed after being struck by a massive cargo ship, an entirely different kind of disaster with construction workers among those affected. The cause there was different, a ship collision rather than a hidden design flaw, but news coverage of that disaster repeatedly reached back to I-35W as the reference point for what happens when a single structural element gives way with no redundancy behind it. 2 very different failure stories, 17 years apart, kept getting told side by side because they share the same underlying warning. I-35W has also become a recurring reference point in American infrastructure funding debates ever since, cited by lawmakers and advocacy groups whenever a bridge repair or replacement budget gets proposed and questioned. Report cards on the nation's infrastructure have continued to hand out middling grades for bridge conditions year after year, with tens of thousands of structures still carrying some form of deficient rating today. None of that means those bridges are secretly flawed the way the I-35W bridge was. Remember what that label actually means. But it does mean the funding gap that lets old infrastructure sit unexamined for decades has never fully closed. Inside civil engineering programs across the country, the I-35W collapse is now a standard case study taught alongside a handful of other defining structural failures as an example of what happens when redundancy is treated as optional. Students studying load paths and safety margins spend time on the Gusset Plate calculations specifically, walking through the same math the original 1965 engineers got wrong to understand exactly where the error crept in. It is a deliberately uncomfortable exercise, forcing future engineers to sit with the idea that the mistake could have been made by anyone in that room. That discomfort is what actually changes how a young engineer checks their own work. Plenty of fracture-critical, non-redundant bridges built in the same post-war era as I-35W are still standing and carrying traffic across the United States today. inspected under the tighter protocols that emerged directly from this collapse. Most of them are almost certainly fine, structures with no hidden calculation error waiting inside their steel. The uncomfortable truth this story leaves behind is that nobody can promise which ones with total certainty, because the flaw that brought down I-35W was invisible for 40 straight years, right up until it wasn't. That single fact is why an investigation from 2007 still shapes bridge inspections happening this week, in cities most of us have never visited. What makes the I-35W bridge such a defining case for this channel is not the drama of the collapse itself. It is how ordinary every single decision looked at the time it was made. A design firm trusted its own math. A state agency trusted the design firm. Maintenance crews poured concrete because that is what responsible maintenance crews do. Nobody in that chain woke up intending to put 13 lives at risk, and that is precisely what makes the story worth understanding rather than just watching. The structure did not fail. The decisions did, one reasonable-looking choice at a time, across 40 quiet years. If this is the kind of story you come to this channel for, the paper trail behind the decision instead of just the footage of the aftermath, there are more cases just like this one waiting for you here. From stadiums nobody wanted to towers that sank into ground nobody tested. And if there is a bridge near you that you have never quite trusted, you are not alone. Plenty of people watching probably feel exactly the same way. Subscribe if you want the next investigation the moment it goes up, because every collapse has a paper trail, and there is always another one worth following.